This is SpaceTime Series 21, Episode 30. Coming up on SpaceTime, a glimpse into the heart of an exploding star. A new study examines the mystery of cosmic voids. And the search for Martian life about to begin. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers peering deep into the violent heart of a supernova have discovered a slowly expanding torus-shaped cloud of oxygen and neon surrounding a young neutron star. The findings, reported in the journal Nature Astronomy, are providing new insights into the processes involved in the explosive deaths of massive stars through core collapse supernovae. Stars are balancing acts in hydrostatic equilibrium between the outwards force generated by core nuclear fusion of hydrogen into helium, the process which makes stars shine, and the inwards pull of gravity. As stars age, they produce progressively heavier and heavier elements through a process called nuclear synthesis. For stars like the Sun, that process ends as soon as you reach oxygen and carbon. But for high-mass stars, they continue producing heavier and heavier elements until, that is, they reach iron. And even big stars simply aren't massive enough to generate enough heat or pressure to synthesize iron into heavier elements. And so, without the outwards force of nuclear fusion to balance the inwards pull of gravity, gravity wins. The star's tremendous mass causes it to rapidly collapse inwards, being crushed under its own gravity. And this collapse works right through into the subatomic level, with even the protons and electrons in the star's atoms being crushed together, forming neutrons. The end result is a neutron star, a strange, little understood object with more mass than the Sun, compacted down into a ball just 10 kilometers wide. Neutron stars are the densest known objects in the universe, other than black holes. In fact, just a single teaspoon of neutron star matter weighs more than the entire Himalayan mountain range. When they collapse, they rebound in powerful supernova explosions, bright enough to briefly outshine an entire galaxy. The supernova remnants they produce during their explosive demise pump new elements even heavier than iron into the surrounding interstellar medium, eventually contributing to the formation of new generations of stars, planets, and life. In fact, the iron in your blood, the calcium in your bones, and the oxygen you breathe were all manufactured in stars. Astronomers were studying one of these supernova remnants, known as 1E0102.2-7219, located in the Small Magellanic Cloud, a nearby satellite dwarf galaxy, some 200,000 light-years away, which appears to be orbiting our own Milky Way galaxy. As they examined this 2,000-year-old supernova remnant, they detected an isolated X-ray emitting neutron star with a weak magnetic field hidden deep inside it. It's the first time an isolated neutron star has been detected inside a supernova remnant in another galaxy. Neutron stars are reasonably common, but they're hard to see because they're so small. They're usually identified by their pulsar, a powerful beam of energy, usually in radio waves, which shines like a lighthouse beacon through the galaxy as the neutron star rotates. The authors were attempting to better understand how progenitor stars evolved to form specific types of supernovae. They wanted to get more details on the processes involved in a supernova explosion and the heavy elements produced in these spectacular events. As they examined their data on this supernova, the authors identified a torus, a donut-shaped structure, of relatively cold, slowly expanding gas amid the complex tangle of gaseous filaments deep inside the remnant. The gas in the torus was at room temperature and composed primarily of oxygen, neon and carbon, and appeared to surround the neutron star. It's the first time this type of structure has been identified around this type of neutron star. One of the study's authors, Dr. Ashley Reuter from the University of New South Wales, says the fact that the supernova explosion left behind a neutron star and not a black hole is an interesting discovery in itself. She says it's still not fully understood which progenitors will go on to produce neutron stars and which will produce black holes. For the moment, the best general rule is that stellar masses below the Chandrasekhar electron degeneracy limit of around 1.44 times the mass of the Sun will produce white dwarfs, while those above it will produce neutron stars. And those stellar masses beyond 2.18 solar masses will go on to collapse beyond the neutron degeneracy phase to produce a black hole. But by simply looking at a supernova remnant without being able to detect the neutron star inside it, scientists can't be sure if the supernova produced a black hole or simply a neutron star that's hidden by all the gas and debris within the remnant. So this discovery provides the authors with a direct link between the detected remnant, a neutron star, and its predecessor, the progenitor star. And making such links helps us understand the explosive mechanisms of supernovae. The identification of the neutron star doesn't finish the story. The authors also want to understand the origins of the associated torus, with its oxygen, neon and carbon emissions. Although it surrounds the cooling neutron star, the authors haven't really worked out why the torus is there. They're fairly certain it's related to the supernova explosion and the formation of the neutron star, but they're not sure exactly when, why or how the torus was formed. The material around the remnant suggested the neutron star's progenitor may have been in a binary system with a companion star. However, if that's the case, where's the other star now? Reuters says while single stars usually behave in ways that are easy to predict, when two stars are close to each other, one can dump matter on or strip matter from the other star, making things far more challenging to interpret.
This supernova remnant is an interesting opportunity to study stellar evolution and the late stages of stars as they die, essentially as massive stars explode and create supernovae. And so essentially how this whole story happened was originally one of my colleagues, Ivo Zeitensal, proposed to look at this remnant with an Australian telescope using the WIFE instrument, which is a wide field spectrograph located on the 2.3-meter telescope at Siding Spring. The observations using that smaller telescope revealed some interesting things, including detection of sulfur and things that weren't previously seen before in that remnant. And so we went ahead and, led by Fred Fogt, who works at the European Southern Observatory, we proposed for time to look at this remnant with a much larger telescope, a 8.4-meter telescope located in Chile, using MUSE, which is a multi-unit spectroscopic explorer. And so with that more sensitive instrument, you can go a lot deeper and get more information. And so it was with these MUSE observations that we found there was even more interesting stuff going on, including this sort of ring-like structure composed mostly of oxygen and neon.
And this torus has not been seen before in core collapse supernovae, I take it?
Right. So this particular structure we really needed the MUSE observations to actually bring it out of the data. Essentially, we were staring at it before with WIFE on a smaller telescope and other, this remnant was actually observed several times before by other people, but this particular ring structure was not really noticed. And so it's only with the MUSE data that we were able to say, hey, this ring looks pretty interesting. Let's investigate this further. And then upon looking at this data even more deeply, and also using some other data from, the Hubble Space Telescope, Chandra X-ray Observatory, already existing data that were basically publicly available. My colleague Liz Bartlett was one of the people mostly working with the X-ray data. We were able to figure out, hey, look, it looks like there's a neutron star located here in this circle, in this torus-like structure. And so that's sort of the big news of this study. Even though people had looked at this remnant for, many times before, no one had actually located the position of the remnant. So we expect these massive stars, when they die, to leave behind either a black hole or a neutron star. But they're still very hard to see, these things. And so this is the first detection of a neutron star, an isolated neutron star outside of our galaxy.
You use the term isolated. What does that mean? Does that mean that it's not in a system with another star, or what?
Right. Yeah. For example, so if you have a neutron star in a double neutron star system, we don't know many of these things. These things aren't extremely common, but they do happen in nature. If they're in a system with another star, for example, either another neutron star, but more commonly, say it's getting mass dumped on it by another normal star, it will shine brightly. You can create X-rays from that, and it'll be an X-ray source. So the fact that it's sort of taking mass from another star will make it shine brightly. But if you have a single neutron star sitting there alone with no other star dumping mass on it or anything, it's going to be close to invisible. It's going to be really hard to detect.
In this particular case, you've got this isolated neutron star, and it's telling you something about its environment.
Right. I mean, essentially, we tend to assume when you have a supernova remnant like this that's from a massive star, because there are different types of supernovae. You have the thermonuclear ones where you get a white dwarf star that explodes, but you have to have another star involved that was dumping matter on that white dwarf for it to be prompted to explode. All the other supernovae that happen come from stars that are really massive, so around 8 times the mass of the sun or greater. These type of really massive stars are quite rare. They live fast and they die young. They burn through their fuel very quickly and explode.
The James Dean syndrome.
Yeah, exactly. Yeah, pretty much. So a lot of them, we would expect in many cases you're going to have a neutron star left behind. They might in some cases make a black hole, but it was sort of ambiguous. We can't really say for sure what remnant was left behind without any real evidence.
That's Dr. Ashley Reuter from the University of New South Wales. And this is Space Time. I'm Stuart Gary. A new study has discovered that the gas inside giant cosmic voids is hotter than it should be. The findings, reported in the journal Physical Review D and on the pre-press physics website archive.org, speculate that the gas in the voids may be heated by jets emanating from supermassive black holes. The large-scale structure of the universe is composed of a cosmic web made up of strands, filaments and connecting nodes full of galaxies, galaxy clusters and superclusters. These surround vast near-empty voids. The research team, led by David Alonso from Oxford University, were able to study the gas in these mysterious pockets of nothingness using observations by the European Space Agency's Planck spacecraft of the cosmic microwave background radiation, the energy left behind by the epoch of recombination around 380,000 years after the Big Bang. This leftover heat from the Big Bang has now cooled down to just 2.7 degrees above absolute zero. But the cosmic microwave background radiation isn't uniform, instead comprising slightly hotter and slightly cooler regions. These temperature variations are thought to be caused by ever so slight differences in density. And that's important because those denser, cooler regions would have evolved into the filaments of galaxy clusters and superclusters, while the hotter, less dense areas would eventually become voids. And gravity over the intervening 13.8 billion years did the rest, removing gas and possibly dark matter from the voids and bringing it into the filaments. The authors were also using data from BOSS, the Baryon Oscillation Spectroscopic Survey, which maps baryonic acoustic oscillations, pressure wave ripples through the early universe, similar to ripples caused by a pebble being thrown in a pond. Baryonic acoustic oscillations are regular, periodic fluctuations in the denser of visible baryonic or normal matter across the universe. In the same way that Type 1a supernovae can be used as standard candles to measure cosmic distances, astronomers can use the matter clustering of baryonic acoustic oscillations as a standard ruler for length scale in cosmology. By the way, the length of the standard ruler is about 490 million light-years in today's universe. These baryonic acoustic oscillations can be measured by looking at the large-scale structure of the universe, which shows a slight overdensity of matter in some regions. And that's providing astronomers with tools to study the nature of a mysterious force called dark energy, which makes up over 70% of the total mass budget of the universe. The researchers in our study used these baryonic acoustic oscillations to pinpoint the positions of cosmic voids across the universe. The positions of 774 of these cosmic voids were stacked against the cosmic microwave background radiation data, allowing the authors to compare the energy of the cosmic microwave background photons in each void to a model of electron pressure to determine the temperature of gas in the voids. The Planck maps allowed the research team to study the pressure inside these 774 voids by stacking them together and examining them as if they were just one giant void. The team obtained the properties of the gas by analysing how the voids were distorting the cosmic microwave background radiation from the early universe. When a low-energy photon from the cosmic microwave background collides with a high-energy electron in the gas, it loses some of that energy, in the process changing the way the cosmic microwave background radiation looks. The authors found the pressure inside the voids is slightly lower than the cosmic average, but the gas in the voids might be slightly warmer than expected. Scientists speculate that powerful jets generated by feeding supermassive black holes could be pumping energy into the intergalactic gas, helping shape the cosmos. I'm Stuart Gary. This is Space Time. The European Space Agency's ExoMars Trace Gas Orbiter is about to begin its primary science mission, searching for signs of Martian life on the Red Planet. The probe was launched on a Russian Proton rocket from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan back in March 2016, achieving Martian orbit insertion 6 months later in September. But the joint ESA-Roscosmos mission almost came to a sudden end when, shortly after the separation of the Proton launch vehicle's BRISM upper stage, a Brazilian ground-based telescope monitoring the event detected numerous small objects in the vicinity of the BRISM, suggesting the upper stage booster may have suddenly exploded just a few kilometres from the Mars probe. Roscosmos was quick to deny any anomaly, and backing that up by making the launch data available to journalists for inspection. Shortly after achieving Martian orbit insertion, the ExoMars spacecraft divided into two vehicles, the Trace Gas Orbiter and the Schiaparelli Lander, which began to descend down to the planet's surface. Sadly, however, Schiaparelli crashed on landing. Meanwhile, the ExoMars Trace Gas Orbiter began a year of aerobraking maneuvers designed to use the drag caused by the probe's solar array panels skimming the rarefied top of the Martian atmosphere to slow down and gradually circularize its orbit. This transformed the spacecraft's 200-kilometre by 98,000-kilometre highly elongated and elliptical orbit into a standard 400-kilometre high 2-hour circular orbit. After the calibration and installation of new software over the next few weeks, the ExoMars Trace Gas Orbiter will begin its scientific mission. The probe has the sensitivity to detect trace gases making up less than 1% of the red planet's atmosphere. The primary target will be methane emissions in the Martian atmosphere. These have already been detected by the European Space Agency's Mars Express orbiter, NASA's Curiosity rover, and by ground-based observatories on Earth. Even more intriguing, the Martian methane concentrations are seasonal, increasing during the red planet's spring and summer. Martian methane is expected to be fairly short-lived, with a lifespan of around 400 years. That's because methane's broken down by ultraviolet light from the sun, reactions with other chemicals in the atmosphere, and through mixing and dispersal by winds. What that means is that the methane being detected now was likely either created recently or released from an ancient reservoir relatively recently. Most of Earth's methane is generated by biological activity, ranging from microbes to bovine flatulence. But it can also be produced through volcanic, hydrothermal and geological processes. Now, no one's suggesting there are cows on Mars. That would be utterly ridiculous. But the recurring seasonal nature of the methane observations could indicate some form of subsurface microbial activity. In other words, life. The ExoMars Trace Gas Orbiter will be able to detect and analyse methane and other trace gases with a level of accuracy 3 orders of magnitude better than any previous measurements, and it will also be able to distinguish between different possible origins. Its 4 onboard scientific instruments will make complementary measurements of the Martian atmosphere, surface and subsurface, and its camera will help to characterise features on the surface that may be related to trace gas sources. Its instruments will also look for water ice hidden just below the surface, which, along with potential trace gas sources, could guide the choice for future mission landing sites. The Trace Gas Orbiter will also act as a telecommunications relay satellite, providing communications links for NASA's Opportunity and Mars rovers on the surface, as well as the planned arrival of NASA's Mars InSight lander later this year, and for ESA's ExoMars rover and surface science platform mission slated for March 2021. Preliminary relay tests with NASA's rovers were conducted in November 2016, shortly after the orbiter's arrival at Mars. Eventually, it'll provide multiple data relay connections each week. This is SpaceTime. I'm Stuart Gary. India has lost contact with its just-launched GSAT-6A telecommunications satellite. The 2,140-kilogram spacecraft was launched just a few days ago aboard an uprated version of India's most powerful rocket, the Geosynchronous Satellite Launch Vehicle, or GSLV, from the Satish Dhawan Space Centre in the southern state of Andhra Pradesh on the Bay of Bengal coast.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, plus 2, plus 3, plus
L40
4,
ignition
plus 5 seconds.
nominal, S139 ignited, and vehicle lifts off from the launch pad.
Tracking.
So vehicle liftoff normal, and performance of L40s and S139 has been indicated as normal.
First stage performance normal. First stage performance normal.
So 52 seconds into the flight, the vehicle has crossed the atmospheric phase, which is a very critical phase. Right now it is
plus
at
1 minute.
11 kilometers. And as per the flight sequence, we will have the burnout of S139 stage at 110 seconds when the vehicle would have reached an altitude of around 42. So at 75 seconds, performance is very normal in terms of time versus altitude and time versus velocity. So after the S139 burnout, we will have the liquid strap-ons burning for the next 40 seconds. And after the L40 burns out, together the 4 liquid strap-ons and S139 will get separated at 151 seconds. So we are at 100 seconds exactly, altitude around 35 kilometers and a velocity of 1.5 kilometers.
S139 burnout normal.
So we just heard the announcement. S139 was burnt out at 109 seconds.
First stage performance
कुछ ही
normal.
क्षणों में
So the event.
L40 engine shut off.
Yes, L40 engine has been
Second
shut off.
stage ignited.
At 149 seconds, the second stage has been ignited. The first stage separation successfully completed at 152 seconds.
अलग हो चुका
Second
है.
stage performance normal.
So we just heard the second stage performance is normal. The flight time is 185 seconds and the vehicle has reached an altitude of around 97 kilometers. The next very important event that we await is at 225 seconds, which is around 30 seconds from now, when the vehicle would have reached an altitude of 115 kilometers, when the heat shield or the payload fairing separation would happen. Right now, heat shield is protecting the spacecraft from the dense atmospheric phase. It has crossed from liftoff to the space. So 215 seconds, another 10 seconds to go before we have the payload fairing separation.
Payload fairing separated.
Payload fairing successfully separated at 226 seconds.
The locally built GSAT-6A satellite flying on a locally built GSLV launch vehicle was supposed to provide a showcase for India's growing prowess as an advanced spacefaring nation. The GSAT-6A was equipped with S and C-band transponders designed to provide mobile communication services for the Indian military across the subcontinent for at least the next 10 years. The spacecraft was also meant to be a technology demonstrator, showcasing advanced space hardware such as a 6-metre unfurlable S-band antenna. 17.5 minutes after its smooth, trouble-free launch, the GSAT-6A was deployed into a geosynchronous transfer orbit ranging from a perigee or nearest point to Earth of 169 kilometres out to an apogee or furthest point from Earth of 36,693 kilometres. Over the next few days, the spacecraft used its liquid apogee rocket engines to circularise its flight path into a geostationary orbit. However, as the satellite prepared to undertake its third orbiting manoeuvre, communications suddenly dropped out. Mission managers have been trying to re-establish contact ever since. The mission was the 12th flight for the GSLV and the 6th using the rocket's locally developed cryogenic upper stage. Meanwhile, just days after the communications shutdown, India successfully launched a new satellite for its indigenous regional navigation system, the IRNSS. The new bird will replace a faulty satellite 7.5 months after its intended replacement was lost during a launch. The 45-metre-tall Polar Satellite Launch Vehicle, or PSLV-XL, blasted off from the Satish Dhawan Space Centre, carrying the 1,425-kilogram IRNSS-1I satellite into orbit.
Event 634 complete. RCT Barrow.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, plus 2, plus
So,
3, plus 4.
Vehicle
plus
has
5
lifted
seconds.
off from the first launch pad.
Liftoff normal.
Liftoff normal has been announced by the Range Operation Director.
R2 tracking.
P3 tracking. R3 tracking. P2 tracking. First stage
गहन
performance
अंधकार
normal.
में
Airlift
और
strap-on
गर्जना
ignited.
Ground lead strap-on has been ignited. So as I was mentioning, we had the ignition of the solid core stage for strap-ons, which was followed by the ignition of the air lead strap-on at 25 seconds. We are almost 43 seconds into the flight now, and the
First
vehicle,
stage performance normal.
first stage performance is normal. The altitude is around 12 kilometers. So we are through the atmospheric phase of flight right now, and
Plus 1 minute.
the next event we wait for is the separation of the ground lead strap-on, which should happen at 70 seconds. Yes,
Ground
the
lead
ground lead
strap-on separated.
ground lead strap-on has been successfully separated at 70 seconds. The vehicle is at an altitude of around 30 kilometers now. The next event will be the separation of the airlit strap-on at 92 seconds now. Another 5 seconds to go before we hear this announcement for separation of the airlit strap-on.
Airlit strap-on separated.
Yes, airlit strap-on has been successfully separated at 92 seconds. And we will have the separation of the first stage coming at 110 seconds now. A plot of the altitude and velocity, a very close match. Yes,
First stage separated, second stage engine started.
First stage has been successfully separated at 109 seconds. Second stage ignition has been confirmed. And the vehicle is right now at 70 kilometers, 126 seconds.
Second stage performance normal.
And the second stage of the flight will be approximately for 150 seconds. And during this time, we will have the separation of the payload fairing, which should happen at 203 seconds. We are at 142 seconds right now.
Second stage performance normal.
So 197 seconds. Nominally, the payload fairing separation time is at 203 seconds.
Payload fairing separated.
Payload fairing has been successfully separated.
And locally as NAV-IC, which means navigation with Indian constellation, the system uses 7 satellites, 4 in geosynchronous orbit and 3 in geostationary orbit. The Indian Space Research Organisation has 9 more missions on this year's manifest, including another mission to the Moon slated for launch towards the end of 2018. You're listening to Space Time. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Well, it's now official. One of the planet's most important climate change regulators, the Atlantic Meridional Overturning Circulation, or Gulf Stream, has hit a new record low. The findings, reported in the journal Nature, used direct measurements and computer models to show that the Gulf Stream has slowed down or weakened by about 15% since the 1950s. A decline in the Gulf Stream from the mid-20th century onwards is one of the key features projected by all global climate change models in response to rising carbon dioxide levels caused by man's use of fossil fuels. The Gulf Stream plays a key role in Earth's climate and is a major component of the global conveyor belt. In its simplest terms, the Gulf Stream's a large-scale system of ocean currents, circulating warm, salty water from the South Atlantic and tropical Caribbean up and along the United States east coast, across the colder North Atlantic, to the British Isles and northern Europe. There, the warm, salty waters cool, releasing heat, and eventually sink into the deep ocean and move back south to repeat the cycle. The Gulf Stream is the reason why the eastern United States, the British Isles and northern Europe don't experience the Arctic cold, freezing sub-zero temperatures of similar latitudes in places like Canada and Siberia. The increased temperatures are now being felt along the northeast United States shelf and in the Gulf of Maine, which has warmed 99% faster than the global ocean over the past 10 years. This in turn has dramatically impacted the distribution of fish and other marine life. A new study says alcohol consumption should be limited to below 100 grams or 10 standard drinks per week in order to lower your risk of death from any cause. The findings, reported in the Lancet Medical Journal, are based on an analysis of over 500,000 drinkers worldwide. The new 10 standard drinks per week limit is significantly lower than the no more than 2 drinks per day which can be consumed within current Australian guidelines. The research found that drinking more than 100 grams weekly lowered people's life expectancy at age 40 by between 6 months and 5 years. The authors found that the more people drank, the higher the risk of a range of life-threatening illnesses, including stroke and heart failure. Archaeologists have uncovered a cache of rare coins dating back some 2,000 years to the time of the Great Jewish Uprising against the Roman Empire. The 1.5 centimetre wide bronze coins were discovered at a dig in the Ophel Cave archaeological site near the Temple Mount in Jerusalem. While several of the coins date to the early years of the revolt, the majority are from its final year, otherwise known as Year 4, dating to around the years 69 and 70. Scientists from the Hebrew University, which is undertaking the dig, say the coins were left behind by Jewish residents who were hiding from the Roman siege of Jerusalem up until the destruction of the city and the Second Temple. The coins are inscribed with the words "for the freedom of Zion," which has been altered to read "for the redemption of Zion," a shift reflecting a change in mood by the rebels during this period. As well as the Hebrew inscriptions, the coins were also decorated with Jewish symbols, including 4 biblical plant species: palm, myrtle, citron and willow, and an image of the goblet that was used for services in the temple. Shards of broken pottery vessels, including jars and cooking pots, were also found at the site. It was during this period that the Romans renamed the Jewish homeland Palestine from its original Israel and Judea, names which date back more than 3,000 years to the time of the arrival of the 12 tribes of Israel into what the Old Testament of the Bible describes as the promised land of milk and honey. It was soon after the Romans quashed the uprising that they instigated their policy of forcibly moving away the Jews to other parts of the empire, in the process allowing nomadic Arabs to move in and occupy the Jewish homeland, the ramifications of which are still being experienced in the Middle East today. The presence of sweet potatoes in Polynesia is often used as evidence of pre-European contact between South America and Polynesia. But new research reported in the journal Current Biology has thrown a spanner in the works of that theory. New genetic evidence shows that the plant species is at least 800,000 years old, far older than even the earliest humans. Instead, the researchers now suggest that sweet potatoes were dispersed naturally around the Pacific and were already there when humans arrived. A new study has found that drinking 3 cups of coffee every day can help protect people from developing irregular heartbeats or arrhythmia. Researchers say there's a long-held perception that caffeine can trigger heart rhythm problems. But this new study suggests that drinking up to 3 cups of coffee a day may be safe for people with arrhythmia and may even have some protective effects. However, researchers do warn that does not include energy drinks containing caffeine. They should still be avoided by people with pre-existing heart conditions, as they contain as much caffeine as 6 cups of coffee in a single drink. The findings are reported in the journal JACC Clinical Electrophysiology. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.